Hey guys, in this video we're going to be discussing dilations. So dilations just means stretches or shrinks. Stretches and shrinks. So what does this mean? So stretching, just think about a rubber band, a same blue rubber band, and we stretch it. So we're using the same rubber band, but we've just changed the way it appears. So this one is the radius, so it's bigger than this. So like the radius and diameter of this rubber band compared to this rubber band, they're the same rubber bands, but they just have a different look to it. They're stretched. One is stretched. Whereas if you have your favorite t-shirt and you put it in the washing machine and it becomes smaller, that's an example of a shrink. So it's the same shirt, you just transformed it. And that's what a dilation is. So let's look at dilations on graphs. So we already just said that stretches and shrinks are dilations. So when does a stretch occur and when does a shrink occur? So stretch, think of the rubber band. So stretch occurs when you have a number that is greater than 0, and it's also actually greater than 1 as your coefficient. 1 as coefficient. For a shrink, the number is greater than 0, so number is greater than 0, but it is less than 1. So numbers like 1 over 2, 3 over 4, and etc. So kind of those fraction numbers or decimals. So let's look at an example. Let's say we had y equals 2x squared. And then let's do this here. Y equals x squared, and then y equals 2x squared. So looking at the equation over here on the left, this is our parent function for a quadratic function. So let's move this a little down. So we have 0, 1, 1, and then 4. 4. Perfect. So with this function over here, we have a dilation. So the number 2 here is greater than 1. So it is greater than 1. So the number is greater than 1, so that means it's a stretch. So we're stretching the graph. So this might seem a little counterintuitive on the quadratic graph, but we can display it numerically as well. So let's take the points. Oh, so here we use the points, so x and y. We use the point 0. We use the point, okay, let's start with -2. -2, -1, 0, 1, and 2. For this side, we got 2, we got 4, we got 1, 0, 1, and 4. But here, when you multiply by 2 for the new y, so let's call this f of g. So for f of g, so function g, don't worry about that. That's just name of function. It's just like y, we're just using f of g. So 2 times -2. So when you plug in -2 for your x value, so 2 times -2, so that's where I'm plugging in the 2, squared. We get, so -2 times -2 is 4. 4 times 2 is 8. And then we get the same thing here. So -1 squared is 1 times 2 is 2. And then 0, here we get 2 and 8. Perfect. So when we graph this, so let's graph it. You're going to have 0, 0, then, and then you're going to have -2, 8. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Let's move the graph a little down. Okay, I think this should be good. Yeah. Okay. And then extend this one. Okay, so we have 0, 0, we have done, and then we have -2, comma 8. So -2, 1, 2, 3, 4, 5, 6, 7, 8. So 8 is right over here. We have 8. Then we have -1, 2. So 1, 2. And then we have 0, 0, and then 1, 2. And then finally we have 2, 8. So the graph is stretched here. So you're stretching it by a factor of 2. Now let's say, so let's take this. Let's do this. So if I go here and I put this graph right on top, you can see how the number 2 has transformed the graph from it being, a normal function to like being stretched out, like it's reaching out for this equation. So let's look at another example. So let's say we have, okay, let's do y equals 1 over 2 x squared. Or let's make this f of h. So ignore this, don't get like stressed by that. That just means y. So we can move this table here. Let's use green this time. So we're going to say f of h. So when you plug the x values into the equation, so 1 over 2 times -2 squared. So you're going to get this equals 2 times 2 is 4 times 1 over 2, that's 2. And then same thing for 1, you're going to plug in -1 here. So -1 squared is 1. 1 times 1 over 2 is 1 over 2. 0, 1 over 2, 2. Perfect. Now if I draw my graph, oops. So I draw my graph right now, like this. Okay. We can plot the points. So -2, 2. And then we have 1, 1/2. So right here, about there. And then 0, 0, 1/2, and then 2. Draw your arrows. Oops. Okay, perfect. So when we compare this to our parent function, which is in blue, you can see that it has shrunk by a lot. Like, you see that there is a significant difference between the parent function and the shrink, and there's a way bigger difference between the parent function and the stretched function. So you can see that. So just remember with dilations, if you have a coefficient that is greater than 1, you have a stretch. But if you have a coefficient or the number that is greater than 0, and it's greater than 0 and it's less than 1, then you have a shrink.